In my last video, I showed the result of this prime number experiment that I've been doing when I carried it out to a further degree. That is to say, I went 50 prime numbers. Well, now I wanted to show some more detail. Okay, so an example of how we can get derived shapes from our tables is here. This is the integers table on the bottom. If, let's say, you divide 3 by 2.5, it's 1.2. 3 by 2.333, 1.285714, and so on. So in other words, if you divide diagonally, you will get a result in the integers table that's in the field. But now, above, in the prime numbers, if you divide diagonally, that result will not appear in the field. Similarly, when we have a table that's constructed of all the numbers except for the primes, we get something else which is quite interesting. Look here, when we try and follow the two axes. It is not like in the other tables where we have an axis that has an even distribution. 2 wanders through here. Find it down here again. It's very irregular. It's what numbers do when you don't have any prime. These shapes are the ones I'm getting at when I describe these functions. That the integers table is like a sphere. That the prime numbers table is like a torus. And that the third table, that of only non-primes, is like the projective plane, or a Mobius strip-like creation, and that all of these generate their own space-time. So what I am saying is that this sphere is the proton, this torus is the electron, and the projective plane is the neutron. As I explained in the movie that I made called Taking People Through the Model, you can discover the next prime numbers by acting as if you were going to create them. The constraints you had were that you had to create the next numbers. And to do that, you need to evaluate them to 1. Or, as we will discover as you go on, you need to find the equivalent of 1. Okay, so we build these because we're building them with the equivalent of, with actually evaluating to 1, and then eventually we have to leave that behind and use the equivalent of 1. And that these electron locations, if we will call them that, also correspond to the electron shell configurations we know from physics. Like, for instance, down here, these are the two S1 and S2. And then you have further P and D locations, and you have interesting happenings where those. So I'm saying that this thing that I'm showing you, where we discover the prime numbers and then we locate them in the integers table, is how light works in this model. And we follow that discovery, and we found that there's a redshift which naturally occurs. That's very interesting. So the point I'm getting at when I introduce these shapes and I say that they're doing things and they have these characteristics where in relation to what kind of numbers they are, that these shapes self-regulate. Now, I don't know if this is true or not, but I'm talking about the theory of how it can be possible that light could move like this, discovering the primes without having to know anything about math to do it. And so I'm speculating that the shapes are self-regulating, that as the shape of the primes table begins to grow over the one axis of the integers table, that it does so according to the geometry, and that the two shapes relate to each other. But I don't know if that doesn't mean that you can't have doping, where you have an occasional non-prime in the primes, or otherwise if you miss a number or whatnot. Because, for instance, the same kind of mechanism might work for the development of atoms. But look, you have a lot of isotopes with atoms where you have numbers of neutrons which are different, even though you get the number of protons the same. So the mechanism could work similarly, and you could have doped prime number fields. It's just I wonder if that's even possible. I don't know.